Welcome to Maths with EJD. In this video, I'll be talking about project duration minimization with linear programming. This falls under a group of problems you can classify as project scheduling and time management. So let's look at that first of all before we go into the main thing for today. So we talk about project scheduling and time management problems. Time management problems. Okay. So project scheduling and time management, particularly, particularly, particularly when there are multiple tasks that need to be completed within a limited time frame, and with resource constraints. Project scheduling and time management are crucial. Yeah, I skipped that. Are crucial. They are crucial in project management. They are crucial in project management. Okay. Particularly when there are multiple tasks that need to be completed within a limited time frame and with resource constraints. Okay. Now, one of the most effective methods, one of the most effective methods one of the most effective methods for solving such problems is linear programming. Linear programming. That is LP for short. So that is, of course, like we already know, a mathematical optimization technique. A mathematical optimization technique that helps allocate resources efficiently. Minimize project duration, or even reduce cost. Okay. In a project scheduling problem, in a project scheduling problem, each task, each task has specific duration and resource requirements. And the tasks may depend on the completion of other tasks. The goal is to organize the tasks to minimize the overall project duration while respecting resource constraints and task dependencies. Okay, so that's how that is. Now let's look at what we actually have for the main focus of this today. That's project duration minimization. So let's look at a project duration minimization problem. Okay. Now imagine that consider the following set of tasks, each with a duration, predecessors, and resource requirements. So imagine that you have task, you have the task, then we have the duration in days, duration in days. Then we have predecessors. Predecessors would be tasks that have to be completed before we do this other task. Then we have the resource requirement in units, whatever that may be. Resource requirement, resource requirement in units. Maybe the machine you have to use or the funds required for the project and all that. So imagine you have projects A, B, C, D, and E. So we have this kind of project, right? And you know, project 8 requires the duration for project A is 4 days, for B it's 3 days, for C it's 5 days, for C it's 6 days, for E it's 2 days, and then for the predecessors. Now, of course, the first project probably it requires nothing before that, so it's the first, and then the second project requires the completion of A. The third project requires the completion of A. The fourth project, project D, requires the completion of projects B and C. And the fifth project requires the completion of project D. Then the research requirements in units will now be like 2, 3, 4, 2, 1. Okay? So the resource requirements in units. All right. Just like we see, task A has no dependencies and requires 2 units of resources, and it takes 4 days to complete. Task B depends on task A and requires 4 units of resource. Task B now depends on task A and requires 3 units of resources, and it takes 3 days to complete. And we see that task C depends on task A and requires 4 units of resources, and it takes 5 days to complete. While task D depends on tasks B and C and requires 2 units of resources and takes 6 days to complete. While task E depends on task D and requires 1 unit of resources, it takes 2 days to complete. So let's formulate this now. So formulating the problem using linear programming. Let me just say problem formulation. Problem formulation. I mean, for this now, if the scheduling is not so big, we can just it's something that can just be done very easily without having to go through all this. But I just want to, establish a format in case that you can scale up for bigger issues. So the objective is to minimize the total project duration while ensuring that all resource and dependency constraints are met. So we can say for the decision variables now, we can say let all xi's represent the start time, the start time of task I, where all the i's belong to A, B, C, D, and E. So that means that XA is the start time for task A, XB is the start time for task B, XC is the start time for task C, XD start time for task D, XE start time for task E. Okay, so we have all of that, and that leads us to, so of course these are the decision variables, right? Then we can talk about the objective function, which is the objective is to minimize the total project duration. Therefore, we want to minimize the completion time of the last task, which is task E in this case. So the goal is to minimize T equals the start time of task E plus, the duration for task E itself is 2 days. So the start time plus 2 days is what we want to minimize as much as possible. So this is because task E takes 2 days. So the project finishes 2 days after XE, because XE is the start time, right? So that is what we want to minimize. Then we have some constraints. So that would be subject to, the first constraint would be the finish time of each task should be greater than or equal to the start time plus its duration. So for instance, task A plus 4. The start time of task A is XA. So it will take 4 days. So the start time plus 4 days should be less than or equal to the start time of task B plus a particular M. Okay? Plus M. Again, the start time for task A plus 4 days should also be less than or equal to the start time for task C plus M again. And then we have that the start time XB plus 3, the 3 days it takes to complete task B, right? So XB plus 3 is less than or equal to XD plus M. Then again, we have XC plus 5 is less than or equal to XD again, XD plus M. Okay, so XA plus 4 less than or equal to XB plus M, XA plus 4 is less than or equal to XC plus M, then XB plus 3 is less than or equal to XD plus M, and XC plus 5 is less than or equal to XD plus M. So all of this now actually are the task duration constraints. Task duration constraints. Okay, but that's not all. So these constraints account for the fact that each task has a specified duration, and the next task can only start once the previous task is completed. Okay, and we know A depends on nothing, right? But B depends on A. C also depends on A. That's why we have those connections between A, B, A, C, and all that. Then we also have other constraints for sure. We have the precedence constraints. For instance, XB is greater than or equal to XA plus 4. XC is greater than or equal to XA plus 4. That means you can only start B after you have finished, after you have finished A, which takes 4 days, right? Then same, you can only start project D after the maximum time it will take to complete XB plus 3 and XC plus 5, because D depends on both B and C. Then you have XE. So you have XE greater than or equal to XD plus 6. So these are the precedence constraints. Precedence. Okay, let's so these are precedence constraints. Okay, So these constraints ensure that task B and task A cannot start before task A is finished, and task D cannot start until both task B and C are finished. So those are actually precedence constraints. Then we still have resource constraints, right? So we need to ensure that the total resource usage at any point in time does not exceed the available resources. So the total resource usage is the sum of the resource requirements of all tasks that are being performed at the same time. For instance, if task A and B are being done simultaneously, the total resource usage will be 2 plus 3 equals 5. Let's define the resource constraint as follows. So see what the resource constraint can be. We have the summation. We have the summation. So it's just summation of resource usage for task in progress at time t. Resource usage for tasks in progress at time t, and all of that will be less than or equal to total available resources. Of course, that's a constraint. Total available resources. So, and that will be resource constraints. Resource constraints. Okay. Now, this constraint should be set for each time point during the project. Then finally, we have the non-negativity constraints as usual, meaning that XA plus XB plus XC plus XD plus XE are all greater than or equal to 0. Okay, so using linear programming, right, we can now solve for the optimal start times of each task to minimize the project duration, ensuring that all constraints are satisfied. So if we take task A now, task A starts at XA equals 0. So we can actually do some kind of manual solution of all that. So task A starts at 0 since it has no predecessor. Task B starts after task A finishes. So XB will be greater than or equal to XA plus 4, and so on and so forth. So this LP model can actually be solved using, as usual, I like to use Python to do this. So let me just go for that. Of course. Yeah, so here we have the project duration minimization with linear programming. And first we used pulp, and everything is presented. All the durations, you can see them in lines 15 to 19. Then you have all the decision variables defined from lines 8 to 12. The problem is set in line 5, and then we have all of that. By the time we just run that, we have this. So XA is 0, XB is 4, XC is 4, XD is 9, and XE is 15. So total, XE is 15. That's it, the start time, of the project. So let's write that out. So that's 0, 4, 4, 9, 15. 0, 4, 4, 9, 15. Okay. And total completion time is 17. So let's go back. Okay. Okay. Well, before I go back even, let me show the other part, right? So that's pulp, right? And then we also have the set in linprog, and we get the same thing, 0, 4, 4, 9, 15 for the tasks, and the total completion time is 17 days. So see how the whole setup is done here based on all the constraints we have set at the other time. So you just want to look through this and try to understand line by line. I mean, we've done a lot of this, so that's why I'm not taking so much time. 0, 4, 4, 0, 4, 4, 9, 15. 0, 4, 4, 9, 15. Okay. So using both pulp and linprog, we get the same thing. So using Python's pulp and scipy.optimize, allow me to just write it this way, linprog, we get XA, the start time for the first project is 0 days. Then XB, 4.0 days. Of course, for obvious reasons, you only start project B after 4 days have been spent on project A. So like that. Then project C is also 4 because project C can be done after project A has been completed. It only depends on A. So 044. Then project D, the start time for project D is actually 9 days because project D can only commence after project B and C have been completed. And project B and C, so adding up all the time, that will be like 9 days, right? Then XE, the start time for project E is 15. But project E takes 2 days, and what we have to maximize is T equals XE plus 2. So T equals XE plus 2. That means you have 15.0 plus 2, and that is 17.0 days. Okay. So that is the solution to that project scheduling problem. And that's all we've got here. So it's straight to the point. Of course, if you have something more complicated, you can actually just use Python to deal with that, and that'll be fine. So if you have not subscribed to this channel, be sure to do that right away. So you can and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know if you want me to solve a problem or teach a topic. Then comment, like and share so that more people can have access to this great learning. I think I would have 2 more videos to go on linear programming, and that'll be all. So I have the next one to record on maybe time management and project scheduling with some constraints too, like that. So watch out for that. Till I see you again, have a great time. Bye.